Picture a tiny neural network, a couple of numbers, a weight or two, and a final score telling you how wrong it is. Now reach in and give one weight the gentlest nudge. Does that score go up or down? And by how much? That single number, how sensitively the loss responds to one weight, is the gradient we need. And a whole network can have millions of them. The naive way would be to rederive the whole loss from scratch for every single weight. On a real network, that's hopeless. Backpropagation does something far cleverer. It's just one idea from calculus. The chain rule pushed backward through the network. So every weight's gradient falls out of work you already did. Let's earn it. One number at a time. The method has a name, backpropagation, and it is the engine that trains essentially every deep network on Earth. Build it once by hand, and it stops being magic. Strip the network down to a single chain of operations. Start with an input x. Multiply by a weight to get a pre-activation z. Push that through an activation function to get a weight of the prediction y hat. And finally, compare it to the true target with a loss L. Left to right, each step feeds the next. Here's the crucial fact. The loss depends on the weight only through this chain. W touches Z, Z touches A touches Y hat touches L. And when one thing depends on another only through a chain, calculus gives us the derivative as a product of the little derivatives along it. That is the chain rule. For our chain, it reads like this. The gradient of the loss with respect to the weight equals the derivative of L by Y hat times Y hat by A times A by Z times Z by W. Four honest factors multiplied together. I like to read it as blame flowing home. The loss knows how wrong it is, and it hands a share of that blame back to Y hat, which passes it to A, then to Z, and finally lands on the weight itself. Compute the values going forward. Carry the blame going backward. 2 passes. That's the whole plan. Before we chain anything, we need the little pieces, the local derivative of each single operation. There are only a handful, and each one is almost embarrassingly simple. Multiplication first. If z is w times x, then the derivative of z by w is simply the other factor, x. Whatever you multiplied by comes straight back out. An identity step, where y hat just equals a, has derivative 1. It passes the signal through untouched. A linear output, y hat equals w2 times h, has derivative w2 with respect to h, again, the other factor. The ReLU activation, max of 0 and z, is a gate. When z is positive, it's a straight line, so its derivative is 1. When z is negative, it's flat, so the derivative is 0. The gate is shut, and no gradient gets through. And the squared error loss, 1 half of y hat minus t all squared. Differentiate it, and the 1 half cancels the 2 from the power, leaving just y hat minus t, the raw error. That clean cancellation is exactly why we keep the 1 half out front. Time for real numbers. Here is our tiny network, and the forward pass just means pour the input in on the left and let every value light up in order until the loss pops out on the right. The input x is 3. That's where we start. Multiply by the weight. Z is w times x, 2 times 3, which is 6. Push 6 through ReLU. 6 is positive, so it passes straight through. Is 6. The output y hat is just so y hat is 6, and the loss, 1 half of y hat minus t squared. That's 1 half of 6 minus 5 squared. 1 half of 1, which is 0.5. Forward pass done. Every value on the chain is known, and the network's current error is 0.5. Now we turn around and walk back. This is the heart of it. On the forward pass, the arrows pointed right. Now we reverse every one of them and send a signal backward. The error signal, written delta. It starts at the loss and flows home to the weight. And at each node, it gets multiplied by that node's local derivative. First, The loss to y hat. The local derivative there is y hat minus t, 6 minus 5, which is 1. So the error signal arriving at y hat is 1. Push it back one more step, from y hat to a. The identity step has local derivative 1. So we multiply our running 1 by 1 and delta is still 1. Now through the real u, from a to z. Remember, z was 6, comfortably positive. So the gate is open and its derivative is 1. Multiply again. Delta stays at 1. If z had been negative, this is where everything would have died to 0. Last step, from z home to w. The local derivative of z by w is x, which is 3. Multiply our running 1 by 3. And there it is. The gradient of the loss with respect to the weight is 3. Every arrow reversed, every node repainted, and the blame has landed. The gradient is 3. And notice we never re-derived a thing. We just reused the running signal at each step. That reuse is the entire point of backpropagation. A gradient is only useful if we do something with it. Here's the rule that does. The new weight is the old weight, minus a small learning rate, eta, times the gradient we just found. The minus sign walks the weight downhill, toward less loss. Put the numbers in, the weight is 2, the gradient is 3, and take a learning rate of 1/10. So the new weight is 2 minus a tenth of 3. A tenth of 3 is not 0.3. So the weight drops from 2 to 1.7 because the gradient was positive, meaning a bigger weight would have grown the loss. We correctly nudged the weight down. One clean step of learning, done entirely by hand. Let's make the payoff obvious with a slightly bigger network. Two weights now. A hidden neuron with a real U, feeding a linear output neuron. The beauty is that one error signal will hand us both weights gradients. Forward pass first. Z is who1 times x, 3 times 2, 6. Real U leaves it at 6. So the hidden value h is 6. The output y hat is w2 times h, 4 times 6, 24. And the loss is 1 half of 24 minus 10 squared, 1 half of 14 squared, which is 98. Now the one signal that does all the work. The error at the output, delta, is y hat minus t, 2e4 minus 10, 14. Compute it once. We are about to spend it twice. Take the output weight w2 first. It's the easy one, a single hop from the loss. Its gradient is delta times its local derivative, which for w2 times h is just h, 6. So 14 times 6 is 84. We reuse delta, and we're done in one multiply. The hidden weight, Wu1 sits deeper, so its blame travels further. Same delta of 14, times the output weight 4, times the real U gate, which is 1, times the input x, which is 2. 14 times 4 times 1 times 2 is 112. Two different gradients, both riding on the very same delta. That is the efficiency backprop buys you. Your turn, one gradient, by hand, a single weight, a real U, and the input keeps the gate wide open. Here are the numbers. X is 4, W is 2, the target is 3. Find the gradient of the loss with respect to W. Pause, do the forward pass, then chase the blame back. I'll wait. Forward pass. Z is 2 times 4, 8. Real U of 8 is 8. Since it's positive, so A and Y hat are both 8. The loss is 1 half of 8 minus 3, squared, 1 half of 25, 12.5. Backward pass. The error at the output is Y hat minus T, 8 minus 3, 5. Then chain it home, 5 times the real U gate, which is 1, because Z was positive, times the input X, which is 4. 5 times 1 times 4 is 20. The gradient is 20. If you got that, and you saw the real U pass the signal through untouched, you genuinely have backpropagation in your hands. Trap 1. Direction. The gradient of L with respect to y hat is not the same as y hat with respect to L. They're reciprocals, not equals. Flip one by accident, and the whole product goes wrong. Read every fraction carefully. Loss on top, the variable underneath. Trap 2, the stray factor of 2, because the loss carries a 1 half out front. Its derivative is just y hat minus t. Forget the 1 half, and you'll drag an extra 2 through every gradient, doubling all of them. Trap 3, forgetting the activation's own derivative. It is fatally easy to chain w2, then x, and simply skip the real u in the middle. But if z were negative, that gate is shut. Its derivative is 0, and the entire gradient along that path must collapse to 0. Never skip a link. And trap 4, the vanishing gradient. A sigmoid's derivative never exceeds a quarter, and out in its flat tails it's nearly 0. Stack many sigmoid layers, and you multiply a chain of tiny numbers together, so the signal reaching the early weights shrinks to almost nothing, and they barely learn. It's the classic reason deep networks reach for ReLU instead. Let's lock it all in. A network is a chain. Input to pre-activation to activation to output to loss. That's the forward pass. Values flowing right. Backpropagation is the chain rule run backward along that chain. The loss gradient for any weight is a product of simple local derivatives, gradients flowing left. The magic is reuse. You compute the error signal delta once at the output and spend it on every weight, instead of rederiving anything. That's what makes it fast enough to train giant networks. And each gradient feeds one small step downhill. New weight equals old weight minus the learning rate times the gradient. Forward, backward, step. Master that loop, and you understand how every deep network on Earth actually learns.